In lesson KP2, you're going to focus on learning a whole variety of probability distributions for discrete random variables. And it's quite easy to get lost in all of the variety of different distributions, particularly if they're just kind of thrown at you without the being directly connected to example and a particular application situation. So what I'm going to do is provide you with sort of the keys to what to focus on and do a little bit of blend here of me doing some demonstration of some of these probability distributions and also putting you into self-study, which I know typically means okay, you'll skim through it and then you'll come back to when you have a homework exercise that keys you to using that one. That's when you'll really get into that particular model and application. So some of the key things to focus on both in some of the demonstrations and then in the reading are how to use the model that you're going to see, and pay particular attention to the context of that model. What kind of situation does it arise, and what are the assumptions? So these three bullets here, context, assumptions, and typical applications, really all kind of come together because the assumptions that we use are there that are embedded in the derivation or development of that particular model are often going to come from the specific application that they're often used for. So there's sort of a nested kind of three different bullets there together. And then occasionally you're going to have some very special properties. Principally, the special property to keep your eye out for is the notion of memorylessness, right? That the model in a sense has no memory. Independent events from every time we, so to speak, throw the dice or flip a coin kind of thing, and does what has happened in the past have any influence on the future? And this one of the crucial key basic principle foundation blocks here is the Bernoulli random variable, which in essence is the kind of random variable where you only have two possible outcomes, 0 or 1, so to speak. Heads or tails would be another typical kind of example, and it doesn't mean that necessarily there's equal likelihood of the 0 or the 1, or the head or the tails, or the failure or success. It doesn't mean equal likelihood at all. It just simply means that there's only two possible outcomes, and you're going to see that notion come back over and over, not only just in the variety of different distributions that you see here. Not all of them are going to be like that, but many of them will start with the basis of a Bernoulli random variable and then work from there. But we'll see the Bernoulli random variable concept come back to us over and over and over throughout the entire course. So having some sort of concrete idea what that is, and that's really more of a self-study to find out more about that. And then what we're going to do from a demonstration standpoint is we will work with a geometric distribution from a demonstration standpoint and a Poisson distribution as well. And by demonstration, I mean there'll be a video capture of me working some problems in the development of those two. Also, in the geometric example, which will be the very first one, pay particular attention to this notion of how we represent data, and some probability notation definitions are there as well. And in particular, what I'm showing you in this geometric demonstration is not just how to use a geometric model, but even far more broader than that in terms of a realistic application of, here's a generic form of the geometric model. Now how do we fit the model to the data? And that is, in that sense, model fitting means how do we estimate what the parameters are? And so that geometric model, which you'll see in one form, a constant a, a constant b raised to some power x, where x is the random variable, how do we figure out what that constant a is? How do we figure out what that constant b is? And you'll see how we set up the constraints of the problem, the basic mathematics of the model. You'll see how we use probability identities to determine what these two parameters a and b are, and we'll also talk a little bit about the notion of where in the population, so to speak, do you fit the model test. And by population in that sense, what I really mean is you've collected data, and so where in that data, in the body of that data, do you really have interest out in the tails? And depending on where your interests are will have a significant influence how you go about estimating what these parameters are. And that notion of parameter estimation is going to come back to us later in Module 6 and 7 as we start to get into not only descriptive statistics, but into how do we go about trying to do that. So this is a little bit of a snapshot in advance of two ways that we go about trying to estimate what those models are, or those parameters are. And then also this Poisson model. Now, also another tool to help you along with this is a table that you will have as a part of your study notes, and it's a partially filled in table. You have different discrete random variable distributions, not all the ones I listed before, but three that are associated very much with the counting notion, and so also very much associated with the Bernoulli random variable as well. Right? And one of the things you might do is you'll be learning, of course, what these equations are all about, both in how I present it and also in your text. But what I would suggest to you is that when I said, how the keys to learning this and organizing your mind around all these different distributions are to put in this box, or a bigger box if you wish, these ideas of how you're going to use the model, the context, the assumptions, any important properties, those sorts of things can go along. Build this yourself, build it in your world, in your applications, where you might see some potential for how you might do that. So in your world of practice, how many successes or arrivals in a fixed time interval? Well, what kind of thing might you be counting as a success or arrivals in a fixed time interval? If you're a civil engineer doing traffic engineering, you might be talking about the number of vehicles that are going to arrive in a fixed time interval. But if you're looking at, say, customers in a store, well, then that's a different kind of arrival. But on the whole, it's still an arrival, right? So that's a guide to begin how to organize your own thoughts. Also, you might want to consider that when we get to continuous random variables, we'll have similar table. In fact, actually what we'll do is we'll stack discrete time and continuous time models right next to each other, because there's some similarities over here in this context of accounting and how we do that versus the discrete and the continuous worlds.